What is good, Year 11 General Mathematicians? Mr. Herman here. This is Lesson 4, Exercise 7D, Pearson's Correlation Coefficient. Pearson is just a statistician, and he invented a very complicated equation just to get one number. That's it, just a number. And what we do with this number is help us determine if there is an association between two variables. The closer this number is to the number 1, the stronger the association is. Now, before I get into this, there's going to be a lot of talk behind this topic, but I want you to put everything within here, with the first part anyways, into a nutshell. All we are doing is looking for a certain number. The equation to get this certain number is very complicated, but you don't need to learn this equation. Your calculator does it all for you. With this number, you then fit this number into a certain category, and that category will describe the type of association between two variables. For instance, if I were to take the example of the very basic one, the height of someone versus the weight of someone. And I created this as a survey. I got this information given to me, and I found out that there is a link between the two. As someone increases their size, their weight will also increase as well. And you can only put this onto a graph, a scatter plot, that we saw in the previous exercises, and then you can talk about the association just by eye. If there's a link, if it clusters close to a line of some sort, if it's positive or negative. But that's all there is to it. That's all you can do. And then Pearson came along and said, you know what? I think there's some maths behind this. I think you can try to figure this out through all the points that have been provided, and we can put this to a number. And this is what this exercise is about. Getting that number, and more importantly, determining what that number can conclude about that association. So if we found a number for height versus weight, we can say, yeah, there's without certainty that there's a strong association or a moderate association. And we'll look into that in a second. But for now, when association is linear, it has to be linear. The most commonly used measure of strength of the relationship is Pearson's correlation coefficient, and this is given by the letter R. It gives a numerical measure of the degree to which the points in a scatter plot tend to cluster around a straight line. Tend to cluster is a big key word, because if we were to put a line of best fit within a cluster, the closer this cluster is to that line, the stronger the association. There are 3 key assumptions when using Pearson's correlation coefficient, and this is very important. The first one is that the data needs to be numerical. There's no point getting 2 variables where one is weight and the other one is favorite ice cream flavor. It doesn't make sense. You can't do that. They have to be both numerical. It doesn't matter if it's continuous or discrete, though continuous does give you more accurate approach, as long as they're both numerical. The second one is that the association needs to be linear. It can't be non-linear. It can't have curves of any sort within the pattern. It has to be a linear association. And the third one, no outliers. It will distort or skew the way that we try to solve for Pearson's correlation coefficient. So if there are no outliers present, that is better. So Pearson's correlation coefficient, let's just put a summary to this. Without even looking at the maths behind it, without looking at how it's derived, let's just try to get some surface level knowledge behind what it actually entails. So right here we have that there is no linear correlation. And when something doesn't exist correlation wise, we just say, look, R is equal to 0 in this case. There might be an R value that you can potentially figure out, but in this case we just say R is equal to 0. Then on the contrary side to that, if there is a perfect positive linear association, we would say that the R value is exactly 1, and it's a positive 1 because from left to right it goes up, and we say that it's exactly 1 because, as you can see here, these lines cluster to these dots cluster to a straight line, and it actually fits on top of our line of best fit, which is highly unrealistic. Okay, but in this case we just want to get a number of some sort, so we say this is 1. And then the other perfect negative linear association, this will be an R value of -1. Now how these R values are determined, you shouldn't know this at this point. Okay, if you're looking at this and you're like, oh, did I miss out on the exercise? What's going on? We're just putting numbers to correlation. Pearson found a way to figure this out. You haven't been shown this yet, so don't freak out. We're just showing you that if it's close to this line, or exactly on the line, your R value is 1. If these points were maybe generally scattered around but very close to the line, then you could say that your R value is 0.99 or 98. So the closer it is to that line, then the higher the value will be until it reaches this limit of either 1 or -1. So in practice, the value of R will somewhere be between +1 and -1. It will never land exactly 1, and it's rarely exactly 0 as shown in these scatter plots below. So as you can see here, we have a positive correlation right here. It's going up from left to right, but it's not exactly on this line of best fit that we can fit in here, but it's somewhat close. So you can say that this here has an R value of 0.915. How you get that value, your calculator gets it, but how you actually get that value is you measure the distance that each line is away through this really tricky formula, okay? Obviously, the further away these points are to the line, the lower the R value is going to be, and it will tend to go to 0. And it will do that until it goes to a negative association, and that's when it becomes negative. So in this case here, we have an R value of 0.767. So because this R value is less than here, this is just indicating that the scatter plot values are more scattered away from this line of best fit. As this R value decreases, your association with the scatter plot tends to stray away, and it's not as strong as it could be in the previous one here. Again, when it's negative, your R value will be negative, but there's also that numerical association. So here it's 0.874, and this is negative, but more importantly, it's somewhat stronger. Not as strong as this association here, but still there is association of some sort. Negative 0.501, a bit more scattery. Here, R is 0.150. This is very close to 0, and you can see here that this is kind of scattered all over the place. So it's safe to say that there's not as strong of association with this here. Now the context, we have no idea what these context is. This could be height versus weight. It could be car price versus car seat price. Who knows? But you can provide an R value no matter what type of numerical variables you get for your EV and for your RV. So these scatter plots illustrate an important point. The stronger the association, the larger the magnitude of Pearson's correlation coefficient, or in other words, the closer it will be to the number either 1 or -1. So Pearson's correlation coefficient measures the strength of a linear relationship with larger values indicating stronger relationships. It always will be a value between -1 and +1. If you get a value 2 or 3 for some reason, you put something into your calculator wrong, or you've figured out the incorrect thing. It's positive if the direction of the linear relationship is going from left to right, and then negative if it's going downwards from left to right. Now there's a little website here, Guess the Correlation Practice, through this Geogebra website. You're more than welcome to visit that. For now, this chart right here, where my face is on top of right now, this right here is very important. Whenever you have anything to do with a correlation coefficient by Pearson and it asks you to describe it, you will be referring to this chart here. Pearson's correlation coefficient can be used to classify the strength of a linear association as follows. So what this chart is, it's giving you different intervals in which the correlation coefficient R can lie in between. So if your R value lies in between 0.75 and 0.99, we didn't put 1 in this case because it never ever has a 1 correlation coefficient. But if it's between 0.75 and 0.99, then it's said to have a strong positive linear association. So before, when we looked at the exercise, when we looked at our actual scatter plot, we had to figure this out through just observing it. If you get some maths behind it and use your calculator to find the R value, then we can say with certainty, 0.75 and 0.99, it has to be strong linear positive association. Between 0.5 and 0.74, there's a moderate positive linear association, and then weak between 0.25 and 0.49. Anything between negative 0.24 and positive 0.24, like this value or this scatter plot here, you would say that there's no linear association. And then again, the inverse of this happens when it is negative. So weak negative linear association, moderate negative linear association, and strong negative linear association. So you get an R value, and this is what I was saying at the start of the video. You get an R value, which your calculator can work out, and I'll show you that in the next video. You associate that R value to one of those intervals, and then you describe that scatter plot based on the description here, okay? All right, that's Pearson's correlation coefficient. The next thing I'm going to show you is the examples over here. And this right here, before I get to this, these are 3 examples. There's a little explanation that we need to go through that talks about correlation and causation. Correlation and causation. So the existence of even a strong association between 2 variables is not in itself sufficient to imply that altering one of the variable causes a change in the other. Okay, so it only implies that this may be the explanation. Alternative explanations to consider include, and there are 3 different considerations. The first one is it may be that both the measured variables are affected by a third and different variable, which is a common response, and the commonality is between the 2 different variables. So say for instance, and you'll see this in the example, but say for instance there was, sorry, I had to think about this one for a second. Say there was a negative linear association, there was a strong one, between buying mittens and a strong positive association, between the amount of mittens that were bought from Kathmandu and the amount of people that were admitted to the hospital for getting frostbite. So is it safe to say that because there is a link between the 2, that if you were to buy mittens, you would get frostbite? That seems counterintuitive, doesn't it? So it's safe to say that there is a third party which, when introduced, affects both of them. And in this case, it's the weather. If the weather's really cold, yes, you're going to get frostbite, and yes, you're going to get you're going to buy mittens from Kathmandu. If you don't, you should really buy mittens from Kathmandu. I'm sure they're really, really good. So in this case, that's where the commonality lies between the 2, because they have a third party that's introduced, and this isn't obvious. Okay, in this case, it was because I made it obvious. I made an obvious example, and the other example is also not as obvious. You just gotta have to think a little bit outside the square. The other one is, it could be that the apparent effect of one variable is caused by a totally different variable, thereby confounding or mixing up the results. And again, I'm going to show you the second example to see how that works. And the other one could be purely coincidental, and maybe just pure chance that the data gathered for the 2 variables seems to be associated, which is a coincidence. And the example will show this, how this works. So let's have a look here. And this question here, we want to look at these different correlations and categorize them from one of the three that I just provided. So this one here, there is a strong positive association between the number of people that uses sunscreen and the number of people that faint. Does this mean that applying sunscreen causes people to faint? Well, no, not really. It doesn't imply that. No, it doesn't imply that. It does not imply that at all. Imply that. It was very delayed. Both of these variables are strongly associated with heat, because people will put on sunscreen when it's hot, but then people will also faint due to heat exhaustion as well. So both of these are strongly associated with heat. Therefore, this is a common response, because the variables have a commonality between heat. Okay, next one. Statistics show that crime rates and unemployment rates in a city are strongly correlated. Can you then conclude that a decrease in unemployment will lead to a decrease in crime rates? There is a confounding variable in this case. There's a confounding variable. And the confounding variable, alright, so the thing that could be linked or may be linked, but we're not too sure yet, is a confounding variable, and this is just the economy of the actual city itself. Okay, because there could be a decrease in unemployment, which will lead to a decrease in crime rates. But it's not just that. There could be other things that could affect that as well. So the decrease in crime rate, in unemployment rather. Decrease in unemployment could decrease crime rate or crime rates. It could decrease, but we don't know this for sure. Don't know for sure. Right, and the last one. It turns out that there is a strong correlation. We have an R value of 0.99 between the consumption of margarine and the divorce rate in the American state of Maine. Can we conclude that eating margarine causes people in Maine to divorce? There must be something in that margarine, but this right here is purely coincidental. Coincidental. I, for the life of me, cannot think of any other thing that could cause or be introduced as a third party or a confounding variable that could cause the people, sweet people of Maine to divorce if they were to eat margarine. Maybe the husband just eats margarine out of the tub, which causes the wife to not like him. So in this case, it's purely coincidental. It's coincidental in this case. And there's a word for this, is spurious. SP. I'm gonna double check to see if that spelling is correct. Yes, spurious. If you type in spurious association into Google, it will come up with all the coincidental associations that you can find within the world, and there's some pretty weird ones out there. And this one that, for this example, was found in one of these websites. And it's true, it is true data. This here, it wasn't made up. There actually is a strong correlation between the consumption of margarine and the divorce rate in the American state of Maine. Weird, but it did happen. Alright, that concludes this lesson for lesson 4, exercise 7D. Check your logbooks, see what you need to do, and I will find you in the next video. Kaleo.